Okay. So maybe this is a good point in time. I'll address the question that was in chat there, and maybe I'll just talk about 7.3.1 very briefly while I'm doing that. So I came up with this sample problem. Absolute value of x is equal to 2x plus 1. And just going to make sure that that appears in the stream here shortly. There we go. Okay. I have a delay on my side, so I don't see things until about 30 seconds after I do them. All right. So let's just go through the solution to this problem. So we would start with the piecewise definition. So one possibility is we would solve x equals 2x plus 1. And the second possibility is we would solve negative x equals 2x plus 1. So I kept this problem fairly straightforward. Just rearranging, I'll work with the red equation here first. So just rearranging that slightly. So we would get negative x equals 1, x equals negative 1 as one possible solution. And moving to the blue equation, this would be negative 3x equals 1, x equals negative 1/3 as the other possible solution. Just glancing over my work here to make sure I didn't make any egregious errors, but I think it's okay. All right, so these two solutions could be extraneous or they could be valid. We have to test them back in the original problem, the one that involved the absolute value sign. So any solutions that we find, and if we do this with a quadratic absolute value function, we'd have to test it into the original quadratic that had the absolute value signs, but that's where they're going to be checked. So if I check the one on the left-hand side, this gives me the absolute value of negative 1 equals 2 times negative 1 plus 1. Absolute value of negative 1 on the left-hand side is 1. Looking on the right-hand side, that ends up being negative 1. So that one fails the check. So this would be extraneous. Extraneous because it solved this linear problem of x equals 2x plus 1, but it was not a solution to the original problem of the absolute value of x equals 2x plus 1. So we can discard that solution. It's not valid. On the right-hand side, let's check our solution of negative 1/3. This gives us the absolute value. Let me just be consistent, so we're going to check. So this would be the absolute value of negative 1/3 equals 2 times negative 1/3 plus 1. When I evaluate this one, the absolute value of 1/3 gives me positive 1/3. 2 times negative 1/3 is negative 2/3. When I add that to 1, I get 1/3. So that one is okay. So this ends up being a valid solution to the problem. So in this case, there is only one solution. It's x equals negative 1/3. X equals negative 1 was extraneous because it did not pass the check in the original problem, whereas x equals negative 1/3 did pass that check. Now you may find that every value you check back in the original passes the check, in which case then they are all solutions. So if they had both passed the check, they'd both be okay. Or you might find that none of them pass the check, in which case there are no solutions. Just answering on my stream, I am going to save this to the classroom stream as well, so you will be able to watch it at a later date. So you can go back and pause me and things along that lines. But what I'll probably do is edit out the 6 minutes of technical difficulty at the start. So I hope that answered the question about where to check it. The place that you're checking it is always this original problem that you started with. And then you use your piecewise definition in order to find the solutions, but then you have to go back and make sure that those solutions are valid. I'm just going to see if there's any other live questions before I do a general overview. I'm happy to see 2 questions in the stream. Last week, the only person who attended was one of my students who is currently living in South Korea and woke up at 2:30 in the morning to attend the stream and said it was worth it. So all of you who could have attended it didn't, shame. But if you couldn't attend, it's fine. Maybe I'll cut that out of the video as well. You saw nothing. Nothing happened. Okay, I don't see any other questions in the stream. So I'm just going to go through and do just like a quick overview of everything that we've done in this absolute value unit so far. So let's just very quickly start with 7.1. So this was just absolute value. So your expectations is basically you should be able to evaluate an expression. Excellent penmanship today. An expression with no variables. So we've done a number of problems like this. So perhaps a problem that was something like this. If I were to evaluate that, we start from inside the absolute value sign first. So -2 times -2 would be a +4. So absolute value of -3 plus 4, which would be the absolute value of 1, which would be the absolute value of 1. In this case, it was a positive that we took the absolute value of. But if that had been a -1, when we take the absolute value of it, we change it to a +1. The other thing is that you should be able to make an absolute value equation based on a word problem. And in all likelihood, those will typically involve distances of some sort, or differences in money, things along those lines. So that was 7.1. It was fairly short. And then we did 2 lessons on 7.2. So there was 7.2.1, which was graphing linear absolute value functions. And I guess just looking at something like this, absolute value of 2x plus 1. Given a linear absolute value function, you should be able to find the graph, find the piecewise function, find the x and y intercepts and things like this. So very quickly, how we might go about it is we could find the y-intercept, and that's by making x equal to 0. So it's the absolute value of 2 times 0 plus 1, which is, I think, the absolute... That can't be right. Nope, because it's not. Which is the absolute value of 1, which is 1. So we would have a y-intercept at 0, 1. We would also want to find the x-intercept by making y equal to 0. And I'm just going to save myself some space. Normally I would do this in 2 steps, but I can jump right into 0 equals 2x plus 1. And that gives us 2x equals -1, x equals -1/2. So -1/2 and 0. So something like that. And then we would want to draw the graph. So we have that is y equals 2x plus 1 here. And if we reflect it, which is y equals negative 2x minus 1, we get the other side of this absolute value function. And the reason I put that reflection, normally you don't have to write those things, but often also asked is the piecewise definition. And we can see that in both these cases it's defined by this point of x equals negative 1/2. So 2x plus 1 if x is greater than or equal to negative 1/2, and negative 2x minus 1 if x is less than negative 1/2. So I would presume that given any absolute value linear function here, you should be able to do all the stuff that I've got on my screen. I don't know if I'll do a full example for the next one because those examples end up being a little bit longer. I guess it will depend on time. But I kind of want to get to the new work since I did a bunch of questions on this last week. So 7.2.2. So this is graphing quadratic absolute value functions. So you should be able to graph something like y equals the absolute value of, let's say, x plus 3 squared minus 1. I'm just visualizing that to make sure it would make a good graph. I think it would. Yeah. You should be able to find the x and y intercepts, the domain, the range, possibly the vertex, because you may need it in order to help you find the domain and the range. And you should also be able to do the piecewise function. So I might encourage you to try that one out. It's in slope-intercept form. Oh, goodness gracious. It's in vertex form. So you could very quickly figure out that the vertex of this graph would normally be a negative 3 and positive 1. Nope, a negative 3 and negative 1. So that would end up being reflected above the x-axis. You could find the roots and so forth. So I would encourage you to perhaps try this one as an example. You should be able to find all of the stuff that I have there. And just going through it in my head, I think it should give you one of these types where it bounces off here, as opposed to one where it's just on one side of the axis. Okay. 7.3.1, which is solving linear absolute value equations. And we just did an example, but you should be able to solve for x, which might give you multiple solutions. It's possible that it won't, but it will likely give you multiple solutions. And then you should check in the original absolute value function to ensure they're valid. And I'll just put here, see the first example that I did, where I went through a problem on that. And of course, in my 7.3.1 video as well. All right. Last up, we have 7.3.2. And this is solving quadratic absolute value equations. So you're going to want to solve How am I wording this? Can't quite spit this out the way that I want to, but solve both possibilities. So for example, if it was the absolute value of x squared, that could be x squared, or that could be negative x squared. So you want to get all possible solutions. Which will probably give you 4, but could give you less, but it will probably give you 4. And then you need to check each one. These are the problems that are very, very long. I wanted to do 2 examples, but I had to actually break it up into 2 videos because each problem took me about 10 minutes to solve. So in solving both of these, realize that you've got some different possible weapons. You have the quadratic formula. You have completing the square. And you have factoring or root finding. Any of those approaches are fine. The quadratic formula is perhaps the most direct, and if you want to use that to do every one of your solutions, that's perfectly fine. I think that's usually the one that most people lean on, probably because in a way it's the most efficient of these methods, the completing the square and the factoring. Well, factoring can be impossible. Completing the square can be more difficult depending on how the problem is set up. Quadratic formula always gives you kind of like a consistent amount of work. And that brings us right to the end. So your assignment is going to kind of cover all of the